Good afternoon, this is Schweitzer, and we're going to run a Smart Notes video on some stoichiometry. Now, this is a video that's intended for, let's say, like an advanced placement situation where really content's no different than a regular chemistry class. It's just going to go a little quicker, so we're not going to stop and potentially dive into problem after problem after problem. This is something for somebody who has already probably seen some of this material, but now needs to just rehash it, get it back into their brain, try some problems out, and move along a little quicker. So, first things first, stoichiometry. Alright, this is what we got here. So, basic skills, these are like an absolute must. We want to be able to flip between moles and particles and mass. Okay, so let's start looking at maybe particles and moles here. So atoms are super small, and with that being said, it's somewhat difficult for us as human beings to deal with individual particles. Anytime that we're doing a chemical, worksheet where we're looking at, like, let's say 25 atoms, really, this is something that it's just not really on our daily life scale. It just isn't possible, right? I mean, it just can't. Every breath is just e to the 25th particles, right? It's just so many particles. They're frustratingly small, and there's so many of them that we package it in moles. So in this case, we'll make sure you understand that 1 mole equals 6.022 e to the 23rd things equals 1 mole. And then, of course, every atom has a different composition of the nucleus, or different elements. So we have a nucleus that contains a certain number of protons, a certain number of neutrons. So these things have different masses. And of course, if you have a bunch of these atoms, and then you're going to want to, versus, let's say, another one, which is 3 atoms that are have more stuff in them. Alright, then when I place these on a scale, it's going to weigh more than if I put these on a scale. So, with that being said, mass is deceiving, okay? Not everything weighs the same. And if you have, 1 mole of hydrogen does not equal in mass-wise 1 mole of O2. Now the particles are equal, but 1 mole of hydrogen weighs 2 grams, and 1 mole of this is 32 grams. So it's like 16 times heavier. So in this situation, our relationships for these guys are, first of all, from here to here is just this guy. Okay. For moles to mass, we're using the molar mass. The molar mass is the mass of 1 mole. Alright, and this next page, alright, so let's just show how this is calculated quickly. Alright, so one thing that's really cool about molar mass and this whole setup and the idea of a mole is this whole idea that 1 mole equals 6.022 e to the 23rd. Now that number is going to seem really bizarre. Where did that number come from? Well, they lined it up, that number up, so the masses and grams also align. So let's say, for example, 1 water molecule. How much does a water molecule weigh? Well, in AMUs, it weighs 1.0 AMUs, and there's 2 of them. I'm getting this off the periodic table of the average atomic weight. oxygen is 15.99, and there's one of them. So in AMUs, strict AMUs, now they're referring to in AMUs is the number on average protons plus neutrons. Okay, it's the weight of that whole thing. So together, 16. I'm gonna round that. 16 plus 2 is 18 AMUs per molecule. That means that on average, there's 8 protons and neutrons. We got oxygen 8 protons, and how many neutrons we don't know, but there's 2 protons in one each. So on this thing, I got 10 protons, and on average, that's exact here, right? Exactly 10 protons. And here, on average, I'm real close to 18, so that's 8 neutrons on average. So that's 18 AMUs per molecule. So this number's matched up so nicely so that this also matches grams per mole. 18 grams per mole. Alright, so let's try a couple of how do we do this then? To get your molar mass, okay, and this isn't something we're going to do a ton of practice on, right? This is kind of introducing it, show you an example, and we kind of move along. Alright, so we know that water is 18 grams per mole. That's H2O. Let's try another one. Let's say lithium. Let's go lithium sulfate. SO4. Now this has got a 4 here and a 2 here. So how do I do this one? Alright, so again, you just go to your periodic table and you add up the average atomic weights of these things. Okay? Lithium is 6.94 times 2. Sulfur is 32.0. And then we have the oxygen is going to be 15.9 or 16 times 4. And I simply start adding all of these things up. Alright, so we got 6.94 times 2 is 13.88. 16 times 4 equals 12. 16 times 4 equals 64. And if this is 32, just straight 32. 32 for that guy. So 32 plus 64 plus 13.88, and we're going to get a whopping 109. 109, that's grams per mole, but it also would be, AMUs per atom. Only thing we could see differently here, calculation-wise, was if I had, let's say, parentheses. We'll do one more quick example of that. You should consider trying that on your own. Let's do aluminum hydroxide. Try it out. We'll have some examples of this just momentarily. So now, for this guy, I could add this up, which would be 16 plus 1 is 17, and then multiply it times 3, and then add in the aluminum, which is 26.98. And what do we get here for this guy? We got 17 times 3 is 51. And then the 2 times, this is, okay, I'll read my own writing, 26.9. Alright? And then just one of those, 26.9. So 51 plus 26.9 is 77.9. 77.9 grams per mole. I typically, if it's like 0.90 like that, I might round to 27. But it's up to you. Alright, let's convert these guys over, and you could check your math here as we move along. 2.5 moles to O3. I might just show work and let you get the numbers on your own. We'll see. 2.5 moles. Get rid of moles, and this is really important to show this work. Go to molecules. Alright, 1 mole is 6.022 E to the 23rd. Now, this is a standard relationship that's never going to change. Okay, never going to change. So 2.5. Now at this point, keep in mind mathematically, 2.5 times that base number is going to give us our new base number. And then we add exponents together, but there is no exponent here, so it's just going to be E to the 23rd. Again, you can punch it in your calculator, and you should be aware how to use your calculator, but you also should be aware of the math. So 2.5 times 6.022 is 15.0. 15.0 we'll go with. Okay. Now, that's E to the 23rd. It also would be 1.50 E to the 24th. All I did was multiply my two base numbers together. It's always an option. And it's important that we're not just doing math without understanding it. 1.5 moles of copper atoms to copper atoms. I'm not sure. Okay, yeah, so 1.5 moles. Get rid of moles and go to atoms. Happens to be the type of particle we're looking here. 6.022 E to the 23rd. Again, 1.5 times that value is 9.0 E to the 23rd. Alright, 3 moles of copper hydroxide, 2 moles. Okay, so 3.0 moles. Get rid of moles. We'll go to molecule. We're getting rid of moles of hydroxide. Okay, so moles of hydroxide. Now, in this problem, there's 2 hydroxides in this problem. So basically, I'm kind of going off of a chemical equation that looks like this, producing 1 copper and 2 hydroxides. Sometimes kids like to see that. We're going to get 2 of those guys. So 1 of those gives me 2 of these. And this gives me my moles of hydroxide. 2 times 3. Remember, on top we're multiplying. Top you multiply, bottom you divide. So we're multiplying here. So the answer is just 6.0 moles of hydroxides. And then it wants the actual molecules. Alright, get rid of the moles and go to molecules. Perfect. 1 mole is 6.022 E to the 23rd. Now keep in mind that because this value is so small, how much do we actually use this value in everyday chemistry? Or our AP problems or in class, once we get past this stuff, almost rarely, very rarely do we ever use this number. Why? Because it's too small for us. On an actual applicable basis, it's too small. Alright, 6 times 6.022, so 6 times 6 is 36. But you get the actual number, always estimating, then get your calculator to give you the exact value. 36.1, and that would be E to the 23rd. Again, that number, a math teacher might cringe at that, but I think that's just fine. There's nothing wrong with that. 3.61 E to the 24th is going to give a math teacher a little bit more of a breather, but it's the same value, and it would be molecules of OH negative. Alright, this guy here, molecules of O2 to moles of O2, so pretty straightforward problem. 2.4 E to the 23rd, and just 1 mole to 6.022 E to the 23rd. I'll let you calculate that one out. Okay, this guy here, to mole total atoms of oxygen. Okay, now this one's, oh, hold on a second here, let's back this up here. I didn't read that problem quickly, and it says we're going backwards on molecules to moles. Okay, so 2.4 E to the 23rd molecules, and I want to get rid of molecules. I want to go to moles. This work is really important because it keeps you from making silly human errors. So 2.4 e to the 24th, not 23rd, alright, divided by 6.022 e to the 23rd, and we get 0.39. 0.39. Now keep in mind, when you're doing the math, you subtract the exponents, because we're dividing, and then you divide these two. So 2.4 divided by 6 is about a third, a little more, which is 0.39, and the exponents cancel to 0. So, there we go. This guy now, molecules, 1.0 e to the 23rd molecules of this guy, H2SO4, total atoms of oxygen. Alright, we're in molecules already, so how many atoms of oxygen are present here inside this one thing? For every one H2SO4 molecule, I get 4 oxygen atoms. Alright, 4.0. I don't know why I got 4. It's just 4. But you need the 0 on that. That's the exact ratio. 4. 4 times 1 is just 4 e to the 23rd. Alright? Some basics. Practice so far. Can you do these problems? 50 grams? Okay, practice 50 grams of CO2. Alright? Do you have more or less than a mole? Interesting problems here. So let's add up to how much 1 mole weighs. And that is always, always, always something in your brain. Carbon is 12. Oxygen is 16 times 2. So that's 32 plus 12, 44. Now kids hate it when I make mistakes, which is why I always pencil math things. Do I have more or less than 1 mole? I have less than 1 mole. Convert to moles. So I am expecting a number less than 1. Hold on a second here. 1 mole weighs 44. Do I have more or less than 1 mole? I have more than 1 mole. 1 mole weighs 44. I got 50. I got more than 1. Check your thought process on that. Convert to moles. So I'd be expecting a number more than 1. Alright. 50 grams. Dot line. Get rid of grams and go to moles. This is the molecular weight. This is the molar mass. Molar mass. 1 mole weighs 44 grams. This, of course, is a fraction larger than 1, which is why I got more. 50 divided by 44 is 1.13. 1.13. That would be moles. Make sure you label things. Convert to molecules. Dot line. Get rid of moles and go to molecules. All these problems should be stopped and trying these things. 1 mole, 6.022 e to the 23rd. And I'm going to let you, I will just do it quickly here. 6.022 times 1.13, and I get 6.8. 6.8, and the exponent is going to stay the same, e to the 23rd. Alright, calculate the number of moles of C, of carbon and oxygen in 50 grams of oxalate. Number of moles, carbon and oxygen. Well, first of all, you should realize that the moles are related here. That for every 2 of these, I'm going to get 4 of those. This is always going to be double. That's important to realize. So I could figure out one of them and just do the other one, I guess. So let's go, first of all, 50 grams of oxalate. I'll have to actually convert that to moles first. So 50 grams of oxalate, get rid of grams and go to moles. How much does this thing weigh? So I got the C2O4. That's what the 50 grams is of. So I got to use that molar mass. This is going to be carbon has a molecular weight of, it's got 6 protons. But on average got 12.01 more molecular weight. So in this case, this guy is going to be 12.01 times 2, and this is going to be 16 times 4. So How much is one way? This is going to be 24 plus 64. Use your calculator here if you want. 88 grams per mole. Alright, so 1 mole weighs 88 grams. Do I have more or less than 1 mole? I have less than 1 mole. Do I have less than half a mole? No. Half a mole would weigh 44. That kind of thought process we spend a lot of time on in regular chemistry. Here it's kind of assumed that you're doing that. 50 divided by 88 is 0.56 moles of C2O4. For every one of these, we get 2 carbons, and that is going to be times 2 is 1.13 moles of carbon. For every 1 mole of carbon, we get 2 moles of oxygen. That's the 2 ratio here. Equals 2.26 moles of oxygen. There we go. Keep in mind it's not O2, it's just straight oxygen here. Calculate the mass of carbon in the sample. Okay, let's take these guys out here. 1.13 moles of carbon, and in this case get rid of the moles, and we go to grams. 1 mole is 12.01. 1.13 times 12.01 is 13.56. 13.56 grams. Now, of course, the rest of it should equal 50 grams. And if you're confident, you could just subtract from the 50. Let's do the math here. 2.26 moles of oxygen. 1 mole is 32 grams. 2.26 times 32 is 7. Hold on a second here. That's not 32, that's O2. Catch yourself. So I got, here, look, good learning point here. I got 72. Is that ever going to give me 50? Okay, that catches yourself. These thought processes, understanding the big picture, catch mistakes. It's 16. It's just straight oxygen, not O2. So we got 2.26 times 16, or 15.99, is 36. 36.16. And those should be awfully close to 50. Alright, so let's use this a little bit. Lots of times we want to be able to figure out how much mass is in something. So if I want to know how much mass of silver could be extracted from silver nitrate, I have 2 ways I can solve this problem. And I'm going to introduce this idea of percent composition and a stoichiometric mole version. Both of these things I consider to be standard stoichiometry, and both of them should be used interchangeably whenever you feel like you can use one versus the other one. Neither one should be considered scary. Let's do this mole version first. So essentially my formula is going to be AgNO3. My reaction would be to produce silver ions plus NO3 minus. Now again, we have this problem on a general honors chemistry problem, and kids, they just ask this question, and they a lot of times just write this problem out. So in this case, I have 25 grams of AgNO3, and I want to get rid of this guy, grams, and go to moles of this stuff. Let's add this up. This silver is 107. Silver, yep, 107, plus the nitrogen is 14, plus 3 oxygens, 16 times 3, and you should get 169 grams per mole on this guy. 1 mole is 169. Now keep in mind, do we have more or less than 1 mole? We have less. 1 mole equals 169 grams. What about a tenth of a mole? Well, a tenth of a mole is 16 grams, and we have more than that. So we should expect a number a little bit bigger than a tenth of a mole. So 25 divided by 16, 25 divided by 169 is 0.147 equals 0.147. Notice a little more than a tenth. And then at this point, this is a 1-to-1 ratio to the silver nitrate, which is 0.147 moles of Ag. And then next I convert this back to grams. 0.147 moles, and we'll get rid of moles, and we'll go to grams. 1 mole is not just for silver is the 107, which will give us grams times 107 is 15.8 grams. 15.8 grams. Okay, and that's of silver. Percent composition method is really important as well. We'll have a whole kind of video of how we use that a little more, but here, percent mass is mass divided by of X substance divided by total mass times 100. So this is the mass of silver divided by total mass. So mass of silver is 107. It's right here. And then the total mass is 169 times 100, means that this formula, regardless of sample size, alright, so 107 divided by 169 times 100 is 63.3%. So 63.3% by mass, and that is of silver. Okay, so regardless of the sample size, that's how much I got. Whether it's 10 pounds, 10 million pounds, or whatever, 63% of it is due to silver. So now, how do I do this? Well, I just take the 50 grams and multiply that times your 50 grams times your decimal version, which is 0.633 equals, so a little more than half, times 50 is 31.6 grams here. So these two should be the same. 50 grams times this should be 31. Let's see, so this would be grams is what I'm getting. Alright, so, here's the problem. Oh, wonderful. I don't have 50 grams of this thing, I have 25 grams. I doubled it accidentally. So 25 grams, again, these numbers should be identical. 25 grams times 0.637% is, alright, so 0.633 times 25 equals 15.8, right on the button. 15.8 grams. Okay. Next, and here's a sample problem. Okay. Decide which way you want to do it. Okay. Let's try a quick problem. Let's just do this when you pick one way. I'm going to do, let's do this way. Another example of that one. So PB, Cl2, PB is 208, 209, 207, okay, 207, 207. The chlorines are 35.4, and we have 2 of them. So 35.4 times 2 equals 70, plus 207 equals 277.8. So 277.8. Sometimes I like this method better because I've just done the molar mass. So all I got to do is the percent lead, PB, equals 207 divided by 277.8 times 100 is going to give me my percentage lead. 207 divided by 277.8, and I get 74.5%. 74.5%. Now, this is a linear proportion, so I could just set up a linear proportion where it says, okay, 74.5 is to 100 equals, this is my total mass on the bottom here, so total mass is 50, and cross multiply and divide, you get your answer. It would be the same thing as saying 207 is to 277.8 equals, what is 50 to this guy? It's the same proportion. So you could start at that point too, but times 50 equals about 37.2 grams. 37.2 grams of PV in my sample of 50 grams. So almost, well, 70% of it is due to lead. And we'll stop here for a moment. This is going to move into our next piece, which is on this idea of limiting reactant